Okay, let's go ahead and get started. So, we have officially finished Chapter 7. You can treat that as good news or bad news, which means we'll be moving into Chapter 8 and into Chapter 10. The somewhat good news about that is the reactions that we saw in Chapter 7, substitution and elimination. It's that exact same chemistry that's happening in Chapter 8, and that's the bulk of the chemistry that we're going to be dealing with as far as Chapter 8 goes. So this week we'll ultimately be practicing a lot of substitution reactions, which reminds me, I've got a quiz, which we'll talk about in a second too. So yeah, we should be getting a little bit of practice with those, or rather, you'll be getting practice with those. So if you've got questions about them, it's a good time to ask when we're going through them. Force me to answer questions and we'll kind of see what happens from there. Okay? The homework is posted both on the slides. I'm pretty sure the current draft has them up there. And then I've also posted them to the announcements as well. Okay? So you've got a running tally of everything. I will note, or like to point out, that we're going to temporarily skip section 8.5. because we're going to deal with that after the exam when we start looking at alkene chemistry. And we're going to permanently skip section 8.6 and 8.7. And then in Chapter 10, we're definitely going to skip 10.7 to the end of the chapter. Okay? Those sections I just don't feel are particularly relevant, and I don't want to waste time on things that just aren't going to be important. We looked a lot at mechanisms so far. Chapter 7 was pretty much, the whole thing was pretty much all mechanisms. Okay? And when we're looking at mechanisms, it's all about moving the electrons. Okay? So it's all about finding a source, okay, and moving it to some place that lacks them. That's our ultimate goal, and that's what we were doing when we drew out Lewis structures. For instance, if we drew out the Lewis structure, password, what the hell? So if we looked at CO3 minus 2, okay, we could draw that out. We could pick carbon as our center atom, could draw on our oxygens around it. And we went in to put in our electrons. I'll leave you guys to count them, but you guys should be able to count them out. Could go through and put all of our electrons around, 2 in between each of those bonds, and that would be all of the electrons that we could add to the structure. Okay? And with this Lewis structure, we'd say, oh, well, this one isn't a good Lewis structure because carbon doesn't have its octet satisfied. Okay, so what would we do? Or what did we do when we had this structure?
Make a double bond.
Okay, how did we make that double bond, though?
Take it from one of the oxygens.
We took electrons. Oh, and I erased it. Awesome. We took electrons from one of those oxygen atoms. I can draw faster. And shared with the carbon. Okay, so what we did was took a lone pair of electrons and we shifted it towards the carbon just to stabilize it. And what we ended up drawing in that case we'll say this structure. Thanks, I already got you.
I'm sorry. It's not you. I'm just tired.
It's not you, it's me.
We end up with this structure where we've shifted our electrons in and we form the double bond. Everything's now happy. We've got our octet all set up. Okay. What we've done, okay, that first time that we showed, or that I showed you those arrows, was ultimately what we're dealing with when we're dealing with mechanisms. We're moving electrons. Except when we're moving electrons in the mechanism, we're not looking within the structure saying, oh, my octet's not satisfied. I'm now changing the location of those electrons from being around one atom, and I'm sharing them with another atom. And in the process of that sharing, I'm forming a bond now between molecules. So instead of looking within, we're now starting to expand outside. Okay? And that's ultimately what our mechanisms are doing. Okay? So when we looked at resonance, or in either of these cases, we end up with very similar rules. Okay? You're finding the source in both cases. You're moving the electrons in both cases. In the case of the mechanism, though, you're moving it from one molecule to another molecule. Okay? And in that process, again, we're forming a new bond, much like we're doing with the carbonate resonance. We're forming a new pi bond. When we're dealing with resonance, we have very particular rules with how we can move those electrons because we're trying to avoid doing a reaction. So there's no atom locations changing. Okay? So when we dealt with it in resonance, we're looking at electrons from atom to a bond, bond to an atom, and officially you can go bond to bond. Okay? If you decide to shortcut between those two rules. Okay? When we're looking at mechanisms, what we're going to do is move those electrons across. Okay? We've now, since we're doing a mechanism, we're actually changing the location of atoms. So we're ignoring our rules from resonance, and now we have to decide, are we in an okay situation or not? Okay? So what we'll do is very similar to what we would do with resonance, verify that we have an octet. In most cases, when the octet is not satisfied, then you're going to have to break a bond. And you've got the option of which bonds to break. You can go for pi bonds or sigma bonds. Okay, so those would be your two main choices. So far, what we've looked at is breaking sigma bonds. Okay, those single bonds. So in the case of a substitution reaction, let's see if I can sneak this structure in here. Okay, if we drew in something along these lines where we had our iodide, and we added chloride to this. Okay, if we did our substitution reaction, we could draw on our chloride as our product. And as far as our mechanism went, what we end up doing, or what we have to evaluate for our substitution reaction, is first finding the individual pieces. In the substitution reactions that we looked at so far, we looked at an alkyl halide. So what's one of the first pieces you need to find? Good enough. I was going to go right back to alkyl halide. So if we're dealing with alkyl halides, we've got to find the alkyl halide first, and in particular the halogen, because that's what's changing the chemistry. If we go in on the carbon-iodine bond, iodine we've decided is more electronegative than carbon, which means the electrons in that bond spend most of their time where? Closer to the iodine. So the electrons start to move towards the iodine. What we're drawing is the electron motion. We're not showing the exchange of atoms. We're only showing where the electrons shift. If iodine starts to draw those electrons, what happens to the carbon? It becomes positive. So what we'll want to do, or officially slightly positive, what we're going to want to do is stabilize that positive. To do that, we'll find a negative, or a nucleophile. Okay? The N part of our SN1 or SN2 mechanisms. So what we're going to do is now find that negative charge. In this case, we're looking at that chloride. Why do we pick chloride? Two answers. One, it's the only one there. Okay? We've already picked the alkyl halide. Chloride's the only thing left. It has to be chloride. Okay? Two, why else could we pick it?
Negative charge.
Negative charge. So we'd have to recognize what our nucleophile is. In this case, that's going to be our chloride. We're going to move the electrons. So we'll start our arrow where the electrons are, which is on the chloride lone pair, and we'll move them towards the positive carbon. Okay? And all we're trying to show is, again, the flow of electrons. how are those electrons moving? Okay. Now that we've got our electrons moving, or at least that we've shown them moving, what we'd end up doing is drawing the product. Okay, and I'm going to erase what I just drew there. Come back to that. So we would have to evaluate everything that's changed or not changed. Did I do anything to save the carbon out here? Or how about the next one? Or the next one? Or the one two later? No. Which means when I draw the product, I'd better not get rid of them. Okay? Conservation of energy, conservation of matter, I can't destroy those. So what I will do is draw those atoms on. Okay? Without having changed their character in the process of doing this. What happened to the bond between the carbon and the iodine? Is it there anymore? No. I've broken it. Okay, if we want to get really, really careful, I don't know I can get this fine with it, but I'm going to try. We can draw that iodine in roughly the exact same position, because officially, when we're showing our reactions, what we're trying to show is not the atom motion, but the electron motion. The atom has not moved. It is in the exact same position. But what happened to the electrons between the carbon and the iodide? They're solely on the iodide. So I don't show the bond anymore. Okay? What happened? I'm not going to be able to draw this one without having moved it. What happened to the electrons from our chlorine? I've now started to share those electrons towards the carbon. Okay? I'm not going to like drawing it this way, but it'll work. If I'm sharing those electrons, what have I formed? A bond, so I'll show that new bond. Okay? Now that I've got the atom locations or the bond locations adjusted, I can go through and assign charges. The iodide is now negative, everything else is neutral. Okay? So again, what the arrows are showing is the flow of electrons. We're not moving atoms. The only reason atoms might appear to change is because when we draw out our original structure, it looks ugly. Okay? And we say, well, ugly things look terrible, so let's make it look pretty. So we redraw the structure so that it looks nicer to us. And that's what the textbook's going to do every single time. Okay? Because they want it to look nice, because that way when some professor goes through and looks at the textbook and they say, oh, the pictures look pretty, they go, we're going to make our students buy that. If they looked ugly, they aren't going to make their students buy it. Okay? So it's, yeah, pretty much. Believe it or not. Okay? So when you're going through and drawing these out, try your best to avoid moving atoms, because the atoms are technically not changing places. Okay? When we're drawing out our reactants and our products, what we're trying to show is pretty much the beginning, what happened before everything happened. The arrow in between, that magic arrow, black arrow in between, is saying this is where everything's occurring, and we're trying to represent that as best we can with our mechanistic arrows. Okay? And then after all of that arrow confusion, that's where we end up with our product. Okay? That's the idea behind this. So, what I've got here is a quiz that I will actually grade loosely, so don't stress too much about it. If you've got questions, please talk to the people around you. Raise your hand. I'll give you 10 minutes.
10 minutes? We're going to quiz, but can we use our notes?
You can use whatever you want. Like I said, I'll even come answer questions.
Okay, what's my answer from the one?
Did you take the quiz one last time?
Yes. I took a test.
Oh, just tell us the class.
There was a whole lot of words on it, but pretty much all it's asking you to do, I think we can too many, is to add mechanism arrows to these reactions. Okay? And that second question where it asks for you to draw the product, don't worry about drawing the product. What I'm concerned about are the mechanism errors. Okay? Try and show how each of those individual steps occur. So evaluate your reactant, evaluate the product, find out what changes. How do you have to move the electrons to account for that change?
Are you telling us that we can essentially just ignore this rate decay?
Yes. Not even essentially, you can completely ignore that.
Yeah, that felt good.
Does anybody want a blank one, by the way? You can keep one if you want to take one home.
Yeah, flip that up. Oh, there's no just in case.
Yeah. I will mention that I've already posted it to Canvas under the old quizzes. What's that? We'll see. There's always hope. Is that a question?
Yeah, so with your reactant or your product, that one, yeah, do we have to draw on that hydrogen then? Because
No.
we have it up there.
That hydrogen does not need to get drawn on. Why does that hydrogen not need to get drawn on? It's implied.
Yeah, but it's already in a reactant one drawn on. So we don't have to.
You still don't have to draw it on. Why was that hydrogen drawn on in this case?
So you can use us.
It's there to confuse you. Okay? Because in the elimination reaction, you immediately say, oh, hydrogen, I'm going to grab it. Oh, there it is, I'm going to take it. Be careful. You're evaluating which hydrogen. In that case, that hydrogen was not the best one to go for. Okay? So it's there to kind of fish for that false answer. You need to be aware of those kind of little tricks. Evaluate what you know to be true. You need to somehow stabilize that positive charge. Okay? When we move on, like I said, alcohol, the alcohol chapter in particular, is a lot of substitution and elimination again, so we will be coming through and doing multiple examples with each of these. Okay? But of course, as with all functional groups, as soon as we hit that new chapter, we get all sorts of nomenclature being added onto this. Okay, I was finally able to find my priority of naming list that I found in a previous semester. Each of these functional groups have a class or a priority, how important they are. So if they show up, we would name our compound based on the highest priority group. So if you had a carboxylic acid in your group or in your structure, you would name the compound based on the carboxylic acid. Everything else would get named as a substituent. Okay? The priority of naming here, everything that we've gone through and looked at, is ultimately how you change the ending. Okay, so when we look at alcohols, the E ending, so if we looked at an alkane, there's an E ending. We remove the E and replace it with an OL. Okay, if it was an alkene and an alcohol, so now it's got a double bond in it. Again, we only remove the last E and replace that with the OL. So we'd end up with an alkenol. So you'd have both. Okay? I definitely don't have space to draw examples of it. So we could go through a couple quick examples. If we looked, let's say this structure. Okay. What functional groups do we have? We've got the OH, which is our alcohol. We don't typically classify this as a functional group, but what class would that be? Anybody? We're looking at an alkane. So to go through and name, what we're going to do is find our longest carbon chain first. Where's our longest carbon chain? The alkane. Again, I would recommend circling. Okay, it works even better if you've got different colors. How many carbons are there? 3. So we have prop. It's an alkane, so we'll go ahead with our AN, but before we hit our, well, I'll go ahead and put it on there for the moment. Okay, so we're looking at a propane. We have a substituent on that propane. It's an alcohol. The alcohol takes higher priority. We remove the E and we change it to OL. So we now have a propanol. Where is the substituent? Where is our alcohol functional group? It's at position 2. We end up with 2-propanol. What's the other name? No, can't be 1-propanol. Isopropyl alcohol. Or isopropanol. Why? This shape is the iso group. There's 3 carbons, so it's isopropyl. Okay? You should be aware of those abbreviations. They're going to show up in your homework. I'm trying my best to make sure that they don't show up on your exams. Okay? What happens? We now change this structure. Okay, we still got an alcohol, but now is it an alkane? We've got a double bond, so it's an alkene. What's our longest carbon chain?
5.
Right. So it would be pentene to represent our double bond. Oh. Okay. It's an alcohol, so we kill the E, turn it into an OL. Now things get really messy because we have to specify where our double bond is, and we have to specify where our alcohol is. I dug myself into a pretty big hole on that one. Anybody know the answer?
2, 4.
Oh, sorry, I had a question.
Damn it. You'll probably ask the question I don't want you to ask, but go ahead.
No, my old question I had to go
Oh, sorry.
up. Did you say it could be 1-propanol because of the structure you put, or it can't be at all?
With the structure I put.
Okay, that's
Yep.
wise.
Okay. We have to specify where the alkene is and where the alcohol is.
4.
2 hydroxyl.
So where I would number it is based on your priority of naming. We want the alcohol to have the lowest number.
2 hydroxyl. 4.
Our hydroxide is at, or our alcohol is at position 2. 2 all. Position 2, we have an alcohol. Where's our double bond? 1, 2, 3, 4. Pent for 5 carbons. At position 4, there's an alkene. Position 2, there's an alcohol. Ouch is right, yeah.
So that's the name.
That's one possibility. I'm not sure on the numbering.
This one's very similar. It was in the book, and it did it 3.
So they did it the same way I did it. Actually,
Just putting a number.
you give the alcohol the highest priority,
Right.
okay, because it's a higher priority, which means we want to number our groups, putting our alcohol at the lowest number.
Right. I think where it just got confusing is the 4 splitting up the pentene instead of making it
So
one
make
word.
it 4 pentene.
Oh,
Yeah.
yeah.
For
So you could
pentene.
also write it for pentene 2-ol. Another reason why I don't like nomenclature. All of these are valid ways to organize that.
But hey, since you're the one writing the exam,
That's why I don't ask these freaking questions. You used to ask for examples, so I got to give you an example so you can do the homework.
The second one's kind of similar to what we were already doing before.
Yeah.
So it makes it a little more
Okay.
easier to-
So it's the idea is to process each of those individual pieces and account for each of your names all the way through it. Okay? Again, when you see it on the exam, if you give me a name where you've numbered and you've named each of your pieces and I can draw the structure, I'll give you points, regardless of if it's the official name or not. Okay? What I want to be aware, or what I want to see, is that you know how to change the name for an alcohol, for an alkene, how to number in general, that you're getting the right number of carbons, okay? And as long as I can take your name and turn it into a structure, I'm happy with it. And if you can take the structure I give you and give me a name that may not have the exact organization right, but has all of the pieces, I'll still give you full credit. Okay? So it still requires practice on your part, being able to put these together. I would highly recommend you follow the textbook with most of these. Okay? If we're going to look at an amine, okay, so I put up some other things here. We could see pick a couple of these. The amines are a little bit easier because they almost always get named as amine. So if we look at the lower right-hand corner, I've got methylethylamine. So we can break it into each of those individual pieces. If we have an amine, what do we have? We have a nitrogen. Okay? We know it has a lone pair because it's not ammonium, which would be the salt. We have a methyl, okay, which says that is a substituent on the amine. So, CH3. We have an ethyl, which means it's a substituent on our amine. How many bonds should a nitrogen have? 3. How many bonds are shown? Which means methylethylamine.
The methyl is the two.
Methyl is the single carbon. And I even put the name together wrong. Ethyl should be before methyl.
I was about to say.
Yeah. Okay? So, can you put the individual pieces together into the structure? The textbook is going to throw a whole bunch of others at you. For instance, aniline or aniline. Okay, that doesn't say amine, that doesn't say anything remotely helpful. What is the structure of this one?
How would you know that?
How would you know that? Exactly right. You wouldn't. You'd have to have it memorized. Okay, it's a common name for that structure. Okay. So the main reason why you would need to know that is because its chemistry changes from the standard amine. Do I expect you to have that memorized? No. Okay. Does the book or do the book questions expect you to look that up? Absolutely. Okay. So be aware you might see some weird nomenclature names being thrown at you. Those are referenced in the textbook. Okay. So refer earlier back in chapter 10 to find where it makes reference to them. Okay. Questions about the nomenclature? Okay. As we continue to go through the rest of these functional groups, in fact, we're supposed to cover all of those by the end of the semester. We'll look at how each of those change the nomenclature and how we have to adjust from there. Okay? So, of course I'm going to come back to this mainly because every time I'm helping students, I start to come back and start making references to it and everybody gives me a blank stare. So, we're going to look at it again and again and again until it's beaten into your head. Okay? So, you need to be familiar with the bonds and forces because that predicts the chemistry that comes out of it. Okay? We can look at the interactions between our bonds and forces or the interplay between them to predict physical properties. Melting point, boiling point. Okay? We could take it even further into solubility. That's also a physical property. Okay? How is this going to end up working for us? Well, we look at our structure and evaluate. Do we have covalent bonds, polar covalent bonds, or ionic bonds? So, what are big red flags for each of those? Which one's the easiest to identify? Ionic. What are you looking for ionic? Charges, okay, or ions. If you see an ion, you're looking at an ionic bond. Okay? Dang. What does that mean about the forces? If you have an ionic bond, you're looking at an ionic force. The ionic force is the strongest force, weakest bond. Okay? So if we have an ionic force, it's a very, very strong polar interaction. Why is it polar? Because we have poles, a positive and a negative, official positives and negatives. Okay? How can we identify a covalent bond? Covalent is equal sharing of electrons. So what kind of rule of thumb could we look at a structure and say, boom, that's covalent? Non-polar, that's all true, but how do you see that if I drew a structure? No ions, that's helpful, but that could also be polar covalent. No charges is officially still going to allow polar covalent to classify. Same atom bonds, okay, and carbon and hydrogen. The biggest one for you guys to remember would be the carbon to hydrogen. Why do same atom bonds give you covalent bonds? They're the same. There's zero difference in electronegativity. Okay? So if you see a carbon and hydrogen bond, you should be thinking a covalent bond, which means what type of force? London dispersion forces. So if we looked at how that molecule could interact with a second molecule, we're looking at a London dispersion force. Okay? What's the strength of the London dispersion force? It's very weak. If we only have London dispersion forces in our compound, how tightly would those individual molecules be held together? Barely. Okay, not very, but barely held together. Okay? Between the molecules, they're not attracted to each other. There's no strong attraction because they were neutral to begin with. There's no reason for them to interact with each other. Which means, what would we predict for our melting points and boiling points? They would all be very, very low because we don't need energy to cause them to break apart. We don't have to pull that hard on them. Okay? So we've got the two big extremes, your ions and your carbon-hydrogen. What's your polar covalent going to be? That's the force, so I don't want to hear the force yet. Unequal sharing. When are you going to see unequal sharing? How many of you have the electronegativities memorized? That's what I thought. So difference in electronegativity doesn't help us. Oxygen, nitrogen, halogen. You can read over the top of that, right? We'll share the S. There it is. Shared S's. Okay? So if you find an oxygen, a nitrogen, or halogen in your structure, you now have a polar covalent bond. What does that mean about our intermolecular forces? That means we're looking at dipole-dipole forces. As soon as you see a dipole-dipole force, you should immediately evaluate, can you do hydrogen bonding? To do hydrogen bonding, what do you need to have? Hydrogen bound to oxygen or nitrogen or fluorine officially, not halogens. Okay? How many bonds can fluorine have? One. How useful is fluorine going to be in our hydrogen bonding rule? Not at all. So if you see a hydrogen bound to oxygen or nitrogen, that structure can hydrogen bond. It's a force now to another molecule. Okay? What does this mean about our phase transitions? Well, if you've got a structure, say like an alcohol, okay, or an amine with a nitrogen, so if we go back and look at this structure, this portion of the molecule can exert hydrogen bonding forces. The rest of that structure and our methylethylamine would be our London dispersion forces, or our LDFs. Okay? Which is the strongest force? Hydrogen bonding, which means we would expect the hydrogen bonding to dominate all our physical observations. That's going to tell us something about our boiling points and melting points. That'll tell us about solubility. Is it soluble in water? Well, what structure is water? H2O, which gives us polar covalent bonds, which gives us hydrogen bonding forces. Similar forces like to interact with each other, which means if we have an amine or an alcohol, we might predict them to be water soluble. If they're water soluble, they're likely organic insoluble. Okay? So we can evaluate each of those individual structures to start to pick out reactivity or our physical properties. We can push that to the ultimate extreme and move into reactivity. Okay? That's where you've got those definitions, which again, I insist that you have memorized. You will be tested on those again. Okay? You need to be able to look at an individual reaction and tell me, is it a Bronsted-Lowry acid, base? Is it a Lewis acid or base? Is it an electrophile, nucleophile? Because if you can identify those pieces, you can start to predict and move your chemistry along. Okay? What happened to water in this case? It went from H2O to H3O+. So it gained a hydrogen, which would be defined as a Bronsted-Lowry base, which means what does this species have to do? Has to act as an acid. Okay? Which means we're probably looking for a Bronsted-Lowry, which means this species has to give up a hydrogen. Okay? So by finding each of those individual definitions, we can start to predict what other things need to happen and push it further along and help us figure out what's going on with it. Okay? So far for our functional groups, we've got alkanes, alkyl halides, and now we're adding alcohols and amines to this list. Okay? Your alkanes, if we look at each of the individual bonds, what types of bonds do we have in the alkanes? Sigma bonds, good answer. Covalent, polar covalent, or ionic. Covalent, because we're looking at carbon bound to carbon, same difference in electronegativity. Carbon to hydrogen, we've defined as covalent, which means what type of force? London dispersion forces, which means what about our boiling points and melting points? They're going to be extremely low because they don't want to interact with each other. What does that mean about our reactivity? Not very reactive at all. And as far as you guys have been concerned, they're completely unreactive. Okay? We don't have any of those partial charges or those differences in electronegativity to allow us to do any chemistry. Okay? So those are unreactive. So what did we do? Well, we said, fine, that's not a very fun structure, so let's mess with it. We added a halogen. In this case, what kind of structure how could we name this group? This, whatever that thing is. Yeah, I was afraid you were going to say that. Alkyl chloride. Why is it an alkyl chloride? Because we've got the chlorine there. We could go through and name it based on how many carbons there are. We've got 4 carbons. The chlorine's at position 2, so we're looking at a 2-chlorobutane. What is further complicated about that? That's going to be on your next exam. It's a chiral center, meaning we would have to go through and name that chiral center as R or S. Okay? So you have to be able to look at each of these pieces. I know we start stacking a lot of things on top and on top and on top, and it's only going to get worse. So crack down now and try and make sure you figure out what's happening with each of these things. When it comes to R and S, it's not that big on the test, or any test. I'm not going to test that heavily on it, so don't stress too much about it. Okay? But be aware that's going to make up at least 10% of the exam. Okay? That chlorine comes in highly electronegative, which means what happens to the electrons in that bond? They start to want to transition towards the chlorine because it's highly electronegative, meaning the chlorine becomes partially negative and the carbon becomes partially positive. We've now generated partial charges. Those partial charges can now interact with each other. So if we took multiple molecules and tried to compare them, say, back to an alkane, what would we expect to happen to our melting points and boiling points? They would need to get higher because each of those individual molecules is going to stack to neutralize that charge. Okay? So we're trying to neutralize, and in that process, we've now got a stronger attraction between them. It's going to require more energy to break them away from each other. That also then ups our reactivity. Okay? And thankfully, when we looked at the alkyl halides, we kept it relatively simple. Our chlorine can only have one bond. It's already got it. So that chlorine doesn't really have the ability to go out and do anything else other than just take the electrons from carbon, which means we aren't too concerned about that partial negative. Taken a step further, okay? Once the chlorine took the electrons, would we expect it to react with anything? Should it take hydrogen from anything? Why not? What happens if chloride takes a hydrogen? It forms HCl, which is a strong acid, completely dissociates. So we wouldn't expect chloride to respond in any kind of Bronsted-Lowry fashion once it came off. Okay? So when we look at our reactivity for our alkyl halides, we were pretty much narrowed down to just the electrophilic carbon. That carbon has lost electrons, so it wants more. That's why it's electrophilic, electron-loving. Okay? When we move up to our alcohols and amines, okay, what have we done in this case? Now when we change up to our structure, instead of putting on a halogen, we're putting on an oxygen and technically a hydrogen as well. We're sliding that oxygen in there as well as a hydrogen, which does multiple things, okay, as you can see by the reactivity. Okay, our strongest intermolecular force is going to be hydrogen bonding because I generate that large partial negative on the oxygen, a large partial positive on the hydrogen. So I get a dipole-dipole force. Okay, once I've got that dipole-dipole force, I can evaluate, do I have a hydrogen bound to oxygen or nitrogen? Yes, hydrogen bonding. So now my strongest force is hydrogen bonding. What does that mean about my melting points and boiling points? They're going to go even higher because now I've got an even stronger attractive force between the individual molecules. So it's going to require even more energy to break them apart and away from each other. Okay? What does that now mean about our reactivity? Well, the larger our charges become, what happens to our reactivity? The more reactive it becomes. Okay? If we compare back to our alkyl halides, oxygen versus chlorine, okay, they both are fairly highly electronegative, meaning what's going to happen to that carbon? Partial positive, it should be electron loving. We've got an electrophilic carbon. Okay? How many bonds can oxygen have before it gets really, really unhappy? Rhymes with it's greater than 2, less than 4. 3 bonds. Okay? Which means our oxygen can share those electrons out with another molecule. Okay? That makes things vastly more complicated because if we can share electrons, we're looking at now a nucleophilic oxygen. It can also be Bronsted-Lowry base. Okay? So both of those things fall out of this. We could also look at Lewis base. I didn't put that on there. Okay? Taken even further, not only have we added that oxygen, but we've also added that all-important hydrogen way up at the very top. Okay? That's going to mess things up even further. How polar is that bond? Very polar. Oxygen's taking those electrons away from the hydrogen. If oxygen completely takes them, what happens to the hydrogen? Goes away, becomes H+, and what we're looking at, Bronsted-Lowry acid. Okay? We can go through and do a very similar treatment with the amines. And since I got the time, I might as well deal with it. When we move to the amines, now what we end up adding into our structures, we still have an electronegative element in our nitrogen, but we're also adding 2 more hydrogens on this case. We can go through our intermolecular forces again. Should be the exact same rules that we follow. We end up with hydrogen bonding. What does that mean about our intermolecular forces? They should be higher than, say, our alkyl halides and our alkanes. How should they compare to the alcohols? That one's a little bit trickier. So our intermolecular force we typically base on the strongest force. And we've classified these both as hydrogen bonding. Okay? But if we go all the way back, I think it's just one slide, it's not all that far. Back to our intermolecular forces, remember this is on a color wheel, meaning it's not this is covalent, now it's magically polar covalent, now it's ionic. It's a gradient. We can shift from being covalent and eventually, if we change the polarity enough, we can become polar covalent. If we continue to change the polarity, we become more and more polar until eventually we become ionic. Okay? So the divisions are not strict. They're very kind of loose. Same thing applies to our hydrogen bonding. Okay? How could we make our hydrogen bond interaction more polar? What would we have to do to get to ionic? I need to increase the difference in electronegativity between the 2 atoms. What's the difference? We're looking at oxygen versus hydrogen and nitrogen versus hydrogen. Does the hydrogen change its electronegativity? No. So we're looking at oxygen versus nitrogen. Which one is more electronegative? Oxygen. Which means what about the hydrogen bonding interaction there? It's stronger. If we have a stronger hydrogen bonding interaction in the alcohol, what does that mean about its boiling points and melting points? It should be the highest. Okay, I can kind of put a note on that. Okay. We can go back through and now evaluate our reactivity as well, and that's what we'll end on. We still have that electronegative element, so we still have an electrophilic carbon. That nitrogen still has a lone pair, so it's still nucleophilic. It's still Bronsted-Lowry basic, but you'll notice I did not put in the acidic hydrogen. Nitrogen has changed its electronegativity enough that it is no longer acidic. Okay? That nitrogen-hydrogen bond is strong enough that it's not easy to break. Okay? In which case we don't see the amine act as an acid. It will only act as a base. So amines are an easier class of molecule to deal with than the alcohols because they're less acidic. Okay, so we've limited some of the reactivity. Questions about any of that? I'm sure you have none now since we're late. But make sure you turn in the quiz.